Welcome to my presentation for my Artificial Intelligence MSc project, where I develop an agent that can drive in a simulator using deep reinforcement learning. On the slide here, you can see a general overview of this presentation, where I summarize what I did during the summer, and then in the end is a demonstration of my results. The aims and objectives are divided up so it enables me to learn how to use Carla, how to use Python, how to use TensorFlow. It was so difficult for me, I decided to focus on getting something working. Hence why I aimed at just making a deep learning pipeline and aimed at understanding the principles. I then also, in my literature review, decided to look at neuroscience papers to see how it can accelerate design. And at the end, you can see the 4 experiments that I run to see if my research has paid off. So the learning algorithm for this project is deep symbolic reinforcement learning. It was deep learning as the actor-critic architecture had several layers and it requires several steps to optimize each of the weights. It was trained in both a stochastic and deterministic setting because firstly, an agent would run for 5 episodes a policy and it didn't know what the next stage was, and that was in the simulation. And then the deterministic setting came in every 5 episodes where a video of the simulations would be used and the model would be fed a frame and each set of actions. And an error would be measured to see how well the PPO model correctly guessed the actions used. And we use proximal policy optimization as we feel it should be a continuous action space. It was symbolic learning as I decided to use a convolutional variational autoencoder in order to compress the high dimensional representational into low dimensional features. As instead of using pixels and matrices, I used the latent features produced, which is the probability distributions, 64 to be exact. And it was reinforcement learning as we want the agent to learn through trial and error its own set of policies in order to navigate the world. In my literature review, I decided to cover a diverse set of papers, as it can literally take 2,000 episodes for an agent to turn left or right. With this, I should hopefully accelerate learning. The most important paper is Curious, whereby researchers enable intrinsically motivated agents to establish their own set of goals to achieve certain tasks. And this works very well, and it's used currently by Codevariant with ABB and as well as OpenAI. On the topic of autonomous systems, I covered Google Waymo and their use of ChauffeurNet, where they use imitation learning to teach expert driving behavior. And then I also looked up Jesse Levinson, as he's the current CTO of Zoox, an automotive driving company recently bought by Amazon, and he was part of the team that won the DARPA challenge in 2007. On the topic of neuroscience, I needed to do it in order to understand perception and how it works with computers. So I also covered a neuroscience paper that was the comparative study of novice and expert drivers, whereby they used electroencephalographic signals, galvanic skin response, as well as heart variations to see what state of mind they were in. And the most important takeaway is that expert driving behavior can be identified with higher standard deviations than steering, as well as the fact that novice drivers learned better in landscape environments as they found it more fun, and they could also learn the dynamics of the car. Alongside that, I looked up Andrej Karpathy, the current director of AI at Tesla, and his seminal paper DenseCap, where he combined the idea of language and vision in order to have architectures that could identify and label images a lot more efficiently, as well as convolutional variation autoencoders and their use in power systems to identify partial discharge. And that suits my background in mechatronics engineering. I believe in having a design philosophy for two reasons. First, being that all these self-driving car companies cannot agree how best to approach this problem. And secondly, if you decide to view a problem as several marginal diminishing returns, you can see which ones you're not maximizing and look at an area to develop. So first, we say it's a model-free algorithm, as even Max Planck, the famous physicist, found economics maths hard, as back then they kept on trying to model the world. Secondly, observation data has to be temporal, so we must be using recurrent neural networks. Even the control algorithms I was using and reading in my literature review, they viewed as temporal data. It has to be continuous action, as that's the way vehicle physics works. If you want to get to a certain speed, you need a change in momentum. And in order to have a change in momentum, you need to accelerate an object. And that can be done by the agent learning to throttle a certain amount. And secondly, using discrete algorithms such as eGreedy can lead to drastic action and changes in policy. I also wanted to reduce representation to reflect expert driving, and curious would have been a bit too much for this project, but by having a custom color space and using a much lower dimension of representation, there's a lot less data for this algorithm. And finally, I decided on actor-critic architecture, where the actor gives out a set of actions, which is a behavior, and this behavior is judged by the critic, as the critic is estimating a value function through what the amount of reward it expects, as well as it trying to minimize dangerous behaviors that the actor could be doing. So in order to take action, it learns a policy, which is a probability distribution, and it's actually a density function it's trying to estimate, consisting of the mean and standard deviation. And it does this through proximal policy optimization, where as it's approximating a function, it is looking for the gradients within there, and it does it by maximizing its performance. And so first it runs a policy to get the state action, the new states and the reward gains, and then the critic plays its role of updating its value function for the targeted reward. And finally, the entire action and policy is evaluated to see whether that policy was good and if it needs to be kept. This is a partially observable Markov decision process. It receives an observation, which is a state, from the dashboard camera. And as you can see, here is my custom color space. Below is the convolutional variation autoencoder architecture. Its representation is transported to one dimension. It was previously three. And through it, it's fed the latent features from the fully connected layer instead. And in total, this representation is 64 dimensions long, and it's fed to the actor-critic architecture. And the steering actions range from -1 to 1, and the throttling and braking, positive and negative, is -1 to 1. So we first needed to pre-train our convolutional variation autoencoder, and that was done by setting an automatic agent to drive in a town. And this was done across 5 towns, collecting 5,000 images in total. Then to reflect the non-Markovian nature of the driving world, I would add images that were augmented. So this could include random erasing, blur, and random rotations. And then in order to make my own custom color space, I got the normal images that were of RGB representation. They also collected data from the logarithmic depth camera. I decided to convert the logarithmic depth camera into one representation. I converted the RGB images to the YUV color space. Then from there, I took away the Y component, since identification is only from 2 components, and I combined them both to have my own representation. And from there, you can evaluate it and train it in an environment with a system of rewards and punishments, and the episode would be terminated if there was a traffic infraction. Then evaluations would be run as usual. Of the first experiment was to compare different representations to see what can accelerate learning. Our first representation is just a segmented color space and it's overlaid with LiDAR images. And then our second representation is the DUV color space, as explained previously. But they both have the feature of depth, as a robot needs to perceive and sense in its environment. And from this experiment, it was found that the DUV color space performs a lot better in getting an agent to learn faster. The purpose of this experiment was to see whether we should model our world as having temporal data, since with the multi-layer perceptron, it is just mapping a certain appropriate observation, which it sees as a state, to an action. So the next video frame given, according to that network, is completely separate. But with a recurrent neural network, it will see successive states as a certain action, and that should translate into the appropriate behavior to give out onto our environment. And definitely from our experiments, I can say the RNN works a lot faster. It literally took 5 episodes to learn to stay in the lane, whereas with the multi-layered perceptron, it can take 2,000. The purpose of this experiment was to see if recurrency was needed in both or either of the architectures. And from our experiments, we can say that it does work better in both. One highlight of this experiment is when the critic just had a recurrent neural network. It exhibited a particularly dangerous behavior where it would constantly drive on both the road and the pavement. This is a classic example of the dangers of AI, where I, the researcher, and then the agent may have the same objective of achieving the next checkpoints within a certain amount of time and maximizing our rewards, but our values aren't aligned, since it's probably easier for the actor to use the contrast in the color space to achieve its objective faster, as opposed to devising its own lane contention algorithm. And what the critic has probably done is through the trials beforehand, it's realized that it can maximize its rewards a lot faster, as it can not only stay in the lane for a longer time, but achieve its objective faster if it decides to use the contrast. The objective of this experiment was to see how we can improve the learning rates through hyperparameter optimization and the idea of training in 2 different environments and 2 different reward systems. As explained previously, when an actor is selecting actions and outputting its density function, it's actually searching for a gradient. And initially, as stated in my thesis, I tried to change the learning rates as well as the discount factors, but that led to failure after 100 episodes, as I assumed that it was either stuck in a local minima, local optimums, or it couldn't find the gradient whatsoever. So in the end, I changed only one parameter, and it was found that it did improve the learning rate. And as you can see, the standard deviation of steering may be higher for the first model, indicating that should be our expert system. But as you can see later on, it just went through some catastrophic failure, as seen from the results. So in total, I was able to use principles from neuroscience and other papers to accelerate learning, but there were quite a few missed objectives. For example, I wanted to use the losses suggested from Google Waymo as part of the systems of rules and punishments. I wanted the design to be modular, and it turns out you really can't do that with reinforcement learning. You just put everything into the observation space and let the policy work out over time what to do with its new information. Even adding LiDAR was quite difficult, which I didn't do in the end. And then there weren't, in my opinion, enough good experiments around where a model would be tested on a new environment. In future, though, I would like to use Carla's scenario runner to implement the idea of hierarchical program triggered reinforcement learning agents, where each scenario has separate policies that can be trained individually. So you can match certain states to actions. And then you can complement this with multitask reinforcement, where you have multiple training going on the same neural net in order to counteract the idea of catastrophic forgetting. In the next section, you'll see the video. So this is a demonstration of how you view the spawn points for your agents to collect, or if you want to set certain spawn locational objectives. And then you can see how you view the routes that an agent can go through. In this example, you see how automatic logic-based Carla agent can go around collecting images, and it collects images from both the segmentation camera as well as the logarithmic depth camera. And the reason I spent arguably more time on this is that if you enable the heads-up display, the FPS will drop and it will lag and the agent will just crash. In the next slide, I show you how we In this slide, you see a demonstration of me deploying an agent in an environment. It's not training, it's trying to complete set objectives. And I'm not sure why it's deciding to exhibit dangerous behaviors as well as break every 2 seconds, but that just highlights the other danger of how black box reinforcement learning algorithms are. Thank you for listening.